Hello, if you're watching this on the non-live version, this is a live stream on graphs. So you might want to skip ahead a few minutes until we properly start the class, but welcome. And welcome to everyone who's joined today. Do feel free to say hi in the chat if you're feeling so inclined, just to let me know that some people are here. So we're going to be looking at graphs today, focusing on the Year 12 skills that come up a lot in final exams, often in the context of basically a Year 12 problem, but also connected with a lot of Year 13 techniques as well. And if you want to join in with any of the quizzes today, then do feel free to scan that QR code or go to slido.com, put in that code, and you'll be able to take part in the quizzes then. And we'll just wait a few minutes to give everyone a chance to arrive. But if you're here, thanks for joining. And hopefully you can hear me. Maybe just say, let me know in the chat if you can hear me. That would be helpful, just so that I know I'm not just speaking to myself. Great. Thank you, Alex. Cheers, Paul. So while we wait for people to join, have a go at those questions there. And if you want to join in with the quizzes, then scan the code. Welcome to people who've just joined. Thanks very much for joining. Do go ahead and go to Slido if you want to join in with the quizzes today, and have a go at those questions while we wait for a few more people to join. We're just going to wait a few more minutes for everyone who wants to join. Welcome to all the people who just joined now. We're just waiting a minute or so for everyone to join who wants to join. But have a go at these questions while you wait. All right, going to get started now. So here are some answers to those questions. We'll go over this today, by the way, so if you were not sure about any of this, do not worry, but the sequence of transformations that maps x squared onto this one, that is a translation of 3 units to the right, and then a translation of 6 units down. You could do down and then to the right, doesn't matter. You could also do write it as a vector if you wanted to be. If you wanted to show off, in fact, a vector is a good way of doing it. Okay, and this one here, function has a minimum point of 3 minus 1. State the coordinates of the stationary points of the following, whether they are minimum or maximum. We'll go through all of this, so don't worry if you weren't sure. But this one here, well, that multiplied the y value by 4. This one here multiplied the y value by -1, and it turned it from a minimum to a maximum by flipping it. More on that later. This one here shifted the x value 5 to the right, and it stayed a minimum. This one here multiplied the x value by 2. And this one here, sneaky one, we'll come on to that. Well done if you got this. This one kept the same minimum point here and then it created a new one over there. But we'll explore that in a moment. Okay, so a reminder, if you were here last time you saw this, but if you weren't, then I just wanted to repeat this quickly. I've done analysis on where all the marks are coming from in all of the past papers we have across all the different syllabuses, all the different exam boards. It's very similar for all of them, but across your 200 pure marks, this is where your marks are coming from, like that. We're focusing on the year 12 content now, the stuff that's often just sort of ignored because because you're busy on year 13 stuff. So we're looking at year 12 stuff, but loads of that stuff just gets free revision in year 13. So I'm thinking about these sorts of ones. By the time you've learned year 13 differentiation with your product rule, quotient rule, chain rule, all of that, the year 12 stuff is just naturally revised, and the same with some of these other highlighted ones, which leaves these. Then these are the ones which I'd say get a decent amount of revision naturally in year 13, and these are the ones that don't. Here are the ones that are worth the most marks. We looked at circles last time. We're going to focus on graphs today. Now that's 6 marks across your A-level. Doesn't sound that much. That's 6 marks of just pure year 12 content, but actually it's probably more like 10 when you factor in some of these graph transformation techniques applied to year 13 concepts. We'll look at that as well. So about 10 marks. So like that is a chunky amount of your A-level, and it doesn't get revised that much in year 13. Okay, a reminder. We're going to start with transformations of points. You need to know all of your basic transformations. Your basic transformations are these. They're your translations, your stretches, and your reflections. Anything outside the bracket affects your y values, and it kind of does what you expect. And anything inside the bracket, so if you're essentially just replacing x with, for example, x minus a or x over a, it affects the x value and kind of does the opposite of what you expect. If you see my online course, you'll know I have this slightly lame but kind of fun method for remembering this called the prisoner method. I don't really like it because it doesn't really create any sense of understanding, but people seem to like it. So I'll repeat it here. Your brackets are your prison. You are a prisoner, and you ask yourself the question, do you want to be in prison? No, you don't. Is it good to be inside the prison? No. Is it good to be outside the prison? Yes. So when you see a transformation applied outside the bracket, that is what you want. Your head is going up and down. That tells you you're affecting the y values. And does it do what you expect? Yes. Look, you're nodding your head. It does what you expect. So this really is a translation of A units up as expected. This one here, we are inside the bracket. Oh no, we don't want to be inside the prison. Side to side, this is affecting x values. Does it do what you expect? No. Minus A actually sends it in the positive direction. So slightly silly technique, but there we go. Now, there are actually two new transformations in year 13. If you haven't covered these yet, apologies, but you'll learn it here. But most of you, I assume, will have, and that is your modulus transformations. So we'll look at these as well. But our modulus transformation, when it's outside the bracket, is just making all of our y values positive. And if it's inside the bracket, it does sound a bit more complicated, but we'll explore that in a moment. Okay, let's review this. This is level 1. This is just transformation of points. So if we have a function like this, it doesn't, I mean, it looks like a quadratic, but it actually doesn't matter what it is. We've got these points A and B, and basic question is, where do these points go under different transformations? So try to answer these in your head. I'm going to talk through each of them. We're going to go through all 8 transformations here just as examples. So f of x minus 3 is outside the bracket. So that is one of these. It's affecting y values, and it's taking us 3 units down as expected. So a here is going to drop down to 0, 3. B here is going to drop down, the x value stays the same, the y value drops down to 1. As always, if you've got questions, do just put them in the chat. I can see the chat over there, and I'll try to notice if people ask questions. Okay, if it's inside the bracket, so that is going this way, it's affecting x values plus 2, you might think goes to the right, but it's actually going to go to the left. So we are taking that and we are sending it 2 units to the left, taking it to minus 2 and 6. This one here, we're taking that x value, sending it to 0 and leaving the y value the same. Okay, some stretches here. So it's inside the bracket, so that is a side-to-side transformation. You would expect 2 to be doubling x values, but it doesn't, it halves them. So this one here, that 0, well, that 0 gets halved, but it stays at 0, and the y value is unaffected. This one here, the x value is going to get halved down to 2, and the y down to 1, and the y value is staying the same. A stretch outside the bracket, so that is outside, so that's good. Does it do what we expect? Yes, so it's halving the y values. So the y value here is going to get halved down to 3. The x value gets left alone, so 0, 3. Here, the x value stays the same on 2. The y value halves down to 2. Okay, reflections here. Outside the bracket, okay, it is affecting y values, right? But if we're affecting y values, it actually means it's a reflection in the x-axis. If you're reflecting in that horizontal line, it's the y value which changes from here to here. So every y value just gets multiplied by minus 1. Okay, transformation for inverse functions. Sure. Yes, I will. I'll come on to that. Thanks for that point. So A is going to go, so just a question in the comments asking about transformations of inverse functions. So that y value there gets multiplied by minus 1, and that y value there gets multiplied by minus 1. Okay, then we've got a f of minus x. So it's inside, so it's affecting x values. So it is a side-to-side one, but that is therefore a reflection in the y-axis. So x value here gets multiplied by minus 1, but that does nothing. The x value here gets multiplied by minus 1, and the y value stays the same. Now on to the modulus one. So these are the new transformations that you learn in year 13. So the modulus of f of x. The modulus function, as you hopefully know, takes whatever you put inside it and just makes it positive. So in this case, actually does nothing because it only affects y values because the mod is outside the bracket, but all the y values are positive anyway. So that's actually not going to do anything here. 6 was already positive and 4 was already positive, so that just didn't do anything. This is the difficult one. This is the more complicated one. F of mod x. It is affecting x values, But here's the logic. We're saying if your x value was already positive, then it's going to do nothing. So in fact, well, the 0 is not affected. So like that just stays the same. And in fact, the b stays the same as well. But that doesn't mean nothing is happening to this graph. What's actually happening, if I was to sketch this, is for all of the parts of the graph with a positive x value, we just leave those alone. For anything that had a negative x value, it basically gets deleted. So we keep all of this. And what happens on this side is you basically copy the right-hand side as a reflection. And that's basically because if you were to sub -2 into this function, if the function was y equals f of mod x, well, if you subbed -2 into that, you would be saying y equals f of the modulus of -2. But that's just the same as f of 2. The modulus of -2 is 2. So the y value when x is -2 is just the same as what the y value was when x was 2. And that's why we get this mirror image over here. Okay. There was a question there about inverses. So I'm just going to do it here for space. There's this other transformation you learn in year 13, which is if you've got y equals f of x, and then you want to see what happens to f inverse of x. This transformation is just a reflection in the line y equals x. And the explanation for that is essentially that if you think about how you find an inverse, like let's just recap that. If you had y equals, say, something really easy like 2x minus 1, our process of finding the inverse is swap the x's and y's and then rearrange to get y the subject. And so the inverse there is that. And so since the process of finding the inverse is just swapping the x and y values, that's all you do on your graph. Any x value, any coordinate is just going to swap, these are just going to swap round. And the effect of swapping around your coordinates is effectively just flipping the whole axes on their sides. So if your original function looked like something like that, then your inverse is going to be a reflection in this line. That basically flips the axes round and we get something like that. All right, I want to look at a few more examples of transformations of points, slightly harder ones here. So the graph f of x equals a modulus of x is transformed into this here. So we need to describe a sequence of transformations that transforms f of x into g of x. This is quite a, well, not a very common question, but a slightly common question. So we need to think, what's the order of events here? And the way I'd suggest you do this is starting with f of x and just doing one transformation at a time, working from the inside out. So starting with whatever's closest to x and then working out. So I'd say the first thing is we replace x with x minus 1. So the first thing is an f of x minus 1 transformation. What does that do? Well, that's a translation, and it's a translation of 1 unit to the right. So I could write this in vector form if I like, of 1, 0. Next thing I see is the 3 there. So I'm going to multiply this by 3. So 3, and then, whoops, that should be a modulus, x minus 1. So that's a 3 times f of x transformation. And so what is that? That's a stretch. Scale factor 3. Parallel to the y-axis is the formal way of writing this. Next, I see a negative there. So minus 3 f of x minus 1 equals minus 3 x minus 1. Minus 3 mod x minus 1. So that's a minus on the outside. So that's a reflection in the x-axis. So laying out step by step just guarantees that you're not going to mess this up. This sort of question would be worth 4 marks, 1 mark for each transformation. The final one, how do I get from what I've got here to what I want there? I'm just adding 2. So I take what I have here, add 2 to it, and that gives me the final thing here. I'm just adding 2 minus 3 mod x minus 1. And so that is a translation of 2 up, so 0, 2. And by doing it step by step, I get my sequence of transformations, no errors, and it's like super clear what's going on. So do take the time to like lay it out like that. I see you're asking about inverse one. I'll see if I have time at the end when the session's finished. I know you want to know about that, but it'll take me a little bit off where I want to go. So I will come back to that if there's time. I'll just stay on stream at the end. Okay, part B. Hence, find the coordinates of the maximum point of g of x. So you've got to know here that the modulus function looks like that. Y equals mod x looks like that. So it's got a minimum point at 0, 0. And we can just use this sequence of transformations to basically track where this goes. So how I'd lay this out, I'd say, well, I start off at 0, 0. Then I do a translation 1 unit to the right. So that takes me to 1, 0. Then I do a stretch of scale factor 3 parallel to the y-axis. So I'm multiplying the y value by 3. That does nothing. Then I reflect in the x-axis. Well, it's already on the x-axis, so that does nothing. And then I do a translation of 2 units up. So that's going to take the y value up to 2. And so there's the coordinate of the maximum point. It became a maximum point, by the way, because we reflected it. So we'd end up with a sort of V shape like that. Okay. One more of these. So this is this okay, question is this a typical question that could come up in year 12 exam? Okay, this question here couldn't come up in a year 12 exam because it has modulus functions in it, but it could have just been a different, for example, it could have just been like a quadratic or some other function, but that sequence of transformations absolutely is something that could come up in a year 12 exam. This as it is could definitely come up at the end of year 13. Okay, I want to look at this technique here. This is quite, can look quite fiddly, but it's an incredibly useful technique and is a concept which doesn't really crop up in the textbooks very much, but does come up in final exams. And that is transforming these simple reciprocal graphs onto something that looks like this, which doesn't really look like a reciprocal graph, but in fact is. So I want to show you a technique for how we can show that this is a transformation of that. You could use algebraic division for this, but it's long and a bit awkward and harder than it needs to be. So here's this nice technique for this. The way I start this is I notice that x plus 1 there, if I multiplied that by 3, I would almost have what I have up here. So the top is almost the bottom times 3. What I do is I kind of force the numerator to be the denominator times 3. So I leave the x plus 1 there, and I basically just write the denominator times 3. So 3x plus 3, but of course that's not what it was. It was 3x plus 1, so I do a little correction here. Then I split this up into 3x plus 3 over x plus 1 minus 2 over x plus 1. This is just 3. Like I literally created this to be 3. That is 3 times x plus 1 over x plus 1. So that's just 3. And then this here is 2 over x plus 1. And now I've got a way of transforming 1 over x into this. Here's the sequence of transformations. I start with 1 over x. First thing, what do? I replace the x with x plus 1. So f of x plus 1 is 1 over x plus 1. So that is a translation of 1 unit to the left. So minus 1, 0. Next, I multiply by 2. So that's a 2 f of x plus 1 transformation. And multiplying a function by 2 is a stretch of scale factor 2 parallel to the y-axis. Next, I multiply by minus 1. So that's a minus on the outside transformation, gives me minus 2 over x plus 1, and that's a reflection in the x-axis. And finally, I just need to add 3 to it. So 3 minus 2f of x plus 1, and that gives me the thing which I wanted. And that's a translation of 3 in the y direction. So that is 0, 3. So I just wanted to show you this technique here of taking basically any linear function divided by any linear function and turning it into a transformation of that reciprocal. You could then use that to sketch this. I haven't really given myself enough room, but basically you're just going to start, maybe for the sake of time I won't go through that, but you're just going to take this graph here and apply these 4 steps, right? Move it to 1 unit to the left, stretch it 2 unit, scale factor 2 parallel to the y, reflect in the x-axis, and then move it 3 units up. So it's just this process here which can be very, very, very useful to know that anything in the form of a linear function over a linear function is actually secretly a transformation of 1 over x. Okay, let's have a go at oops. Oh, you know what? Do I have the wrong file here? You know, I do have the wrong file here, which doesn't have my quizzes in it. So hold on a second. I'm going to open up the right file. Give me a moment. And let's open the one where you can actually do the quizzes if you want. Oh, here we go. All right, so have a go at joining here if you fancy. Let's see when this comes up. Yeah, there we go. So yeah, if you fancy joining the quizzes, just join there. Maybe you already have. And let's head over and do the quizzes. Okay. Tap, 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 tap. Let's get to the quizzes. Right. And if this was a faff to join and not many people managed to actually do it, then I will just leave it. But thank you for you guys joining. Okay, so join the quiz whenever you like. Let's have a go at this. So find the coordinates of the point minus 2, 5 under the transformation f of a half x. Okay, let's see results. Okay, most people got that. So that transformation is in the x direction, so it's affecting x values. You would think it would halve them, but it actually doubles them. Okay, how about this one? Find the coordinates of the point -2, 5 under the transformation modulus of f of x. Okay, let's see. All right, that one was a sneaky one. It just did nothing, right? Modulus of f(x) leaves the function alone if the y value is positive, and if it was negative, it would have made it positive, but it doesn't touch the x value, which is why it didn't change that 2 to a that -2 to a 2. All right, double one here. So find the coordinates of the point -2, 5 under the transformation 2 f of x minus 1 minus 7. Actually, there's 3 transformations here. Take a moment to think through what's going on. Okay, let's see what you think. Okay, nice one. So yeah, what's this doing? Starting from the inside, this is a translation of 1 unit to the right. So that's going to take the -2 up to -1. Next, we are doubling the y value. So we've now got -1, 10. And then we're subtracting 7 from the y value, so -1, 3. All right, well done, Terence. That's the Terence who I used to teach. Thanks for joining. Nice to see you there. Well done. Okay, level 2 here. I want to look at some year 12 transformations, but applied to more challenging graphs. So some of these are kind of pushing into year 13 territory, but of course, e to the x is actually on the year 12 spec as well. So here's a kind of question that is quite common. So sketch a graph of 5 minus 2e to the x, including the exact coordinates of intersections with the axes and equations of asymptotes. All right, so this, some people are able to just kind of jump straight to this, but I wouldn't recommend it. I would think of this as a sequence of transformations. And I do something like this. I'd be saying, okay, just start with the basic building block, e to the x, and then think what actually happens to it. Well, it gets doubled, so that's a stretch. And this question is not asking for a sequence of transformations. I'm not going to bother writing this, but mental note that that's just a stretch in the y direction. Then a negative on the outside, so that's a reflection in the x-axis. Then we're adding 5 to it, and that's a translation in the y direction. So I've now got a sort of clear list of what's going on, and I can draw a rough sketch for each of these. So here's what I'd actually suggest doing. Very rough sketch, e to the x. We've got to know what the basic thing looks like. Next, and a useful thing is record the intersection. E to the x crosses the y-axis at 1, and it's got an asymptote of y equals 0, the x-axis. Okay, when we stretch it, what happens? Well, all the y values get doubled. So that 1 goes up to 2, but it's still got y equals 0 as its asymptote. Okay, next is a reflection. So again, these are just rough sketches. So I'm just going to reflect that in the x-axis. So the 2 goes down to a -2, but still that y equals 0 is the asymptote. And now I'm ready to do the kind of the neat sketch, which is going to be this whole thing shifted up by 5 units. So crucially, that asymptote is going to be shifted up by 5 units. Put that in as a dotted line to y equals 5. So my curve is going to be running down here, and that intersect here is going to move up from -2 up 5 units to 3. And so there's my sketch. Now it did say find the exact coordinates of intersections with the axes. So I've got that one. It's 0, 3. I just need to find this one, and I'll do that simply by solving the equation 5 minus 2e to the x equals 0. So 5 equals 2e to the x, and solve. 5 over 2 equals e to the x, and x is ln 5 over 2. And so we've got our exact coordinates here, ln 5 over 2, 0. So those questions asking you to do transformations on things like e to the x, it's very helpful to list those out as a sequence of transformations. Okay, let's have a look at, I'm actually not going to do that one now because yeah, I'm going to move on to this. So this questions like this have actually come up twice now in Edexcel, once in AQA, a few times in the others as well. So this one is I think quite a common one. So the figure 1 shows a graph of p sine qx plus r. So it's just some kind of transformation of sine x. And we've been given relatively detailed graph in radians. And we need to work out what all of these constants are. So I want to give you a little framework for working through these. Now, here's basically the way I'd approach this. I start with the idea of amplitude. So amplitude is just how tall the graph is. Now sine x typically goes, well, typically it does go up to 1, down to -1. So its amplitude here is 2. So, or okay, forget the words amplitude, but it's it basically has a range of 2, okay, from its bottom point to its top point. Now look at this graph, and it goes up to 1, and it goes down to -5. So that's a range of 6. So how do we stretch the graph out from a range of 2 to a range of 6? We must have stretched the graph out by a scale factor of 3. So that means that this p here, that's the one which is doing the stretching in the y direction. That's 3. And there isn't really any working for this. That's pretty much just stated. P equals 3 because of that stretch. Okay, next on to the q. For this one, I need to be thinking about the period of the function. So I know that sine has a period of 2 pi. It takes 2 pi radians to get from the start of the cycle to the end of the cycle. Looking at this one, what is its period? Well, starting here, how long does it take to get back to exactly that point? So up here, down here, that doesn't count because we're in a different point in the cycle. Down here and up here, there, that's the end of that cycle. So that's 4 pi rather than 2 pi. So I know it's been stretched outwards by a scale factor of 2. So what would q need to be to give me a scale factor of 2 in the x direction? Well, not 2, that would squash it in. It's got to be half. Again, there's not really any working I can show other than stating that q is equal to a half. Finally, r. Well, that one's in this question is actually the easiest because I can just say that if it were just 3 sine of half x, it would go from 0 up to 3 down to minus 3, but we're going only up to 1 and down to minus 5. So, and it starts at minus 2. So that's just been moved down by 2 units. It's not going up to 3, it's going up to 1. It's not going up to down to minus 3, it's going down to minus 5. So it's been moved down 2 units, and that tells me that r must be minus 2. So when you're working through questions like this, just try that sequence of thoughts. What is the range? What's the difference between the highest point and the lowest point? And that will tell you what the stretch is that way. Measure the periods and compare that to 2 pi. That will tell you what's been stretched by that way. And then for if anything added on the outside, you sort of compare the highest point to what it would have been without that. Here's a different one. It looks a bit kind of complicated, but we'll be okay. Figure 2 shows a graph of f of x equals a cos x minus alpha plus b. So again, that's just 3 transformations. It's some kind of translation, it's some kind of stretch, and it's some kind of translation. We're told that alpha is between 0 and pi over 2. So let's see if we can find this. Again, we'll start with the stretch by considering the range of the function. Cos, just simple cos, goes from 1 down to minus 1. It's got a range of 2. We go from minus 1 at the bottom up to 7 at the top. That's 8. So that is 4 times bigger than cos normally is, which means a equals 4. All right, for these two, let's have a think. Well, the plus b, we can just compare highest points to what it would have been if it had just been 4 cos of stuff. 4 cos of stuff would go up to a maximum of 4, down to a minimum of minus 4. We go up to 7, so that's 3 more. We also go down to minus 1, that's 3 more than minus 4. That tells me that b must be 3. Finally, I can look at this translation here, and I can think that cos normally starts at its highest point, goes down and up, but our highest point was shifted along a bit. It wasn't here, it was there. So that's a translation of pi over 4. So that tells me that alpha must just be pi over 4, and the minus was already there, which means it is a translation to the right. Okay, so there are some examples of transformations on harder graphs. Let's have a go at this in the quiz. So, cool. So here is a function a sine bx plus c. Find the values of a, b, and c. Is it not showing the options there? It's a little bit hard for you guys to see. I don't know whether it's possible actually on your phones to see. Hopefully you can see the options on your phone. If no one's answering this, then I won't bother with this because that's maybe too big to show. But anyway, I'll give it a moment in case it does work. This is actually a bit of a nasty one. Apologies. This is harder than my examples, but I will go through this. Okay, let's explore. Okay, big mixture of answers there. Ooh. Okay, no one got that one. Let me go through that. I think that's quite challenging. Okay, I start with amplitude. So, okay, sine normally has a range from -1 to 1, so it normally has a range of 2, but I see this one goes from -2 to 4, which is a range of 6. So, looks like A is going to be 3, but hold on, there's a sting in the tail there. Moving on to let's do the C. Well, it doesn't really matter which one. I'll do the C. Let's do B next. So I see that the period of this one is pi, and in sine that would normally be 2 pi. So it's being squashed in by a scale factor of 2. So that means that B is 2. Finally, the highest point of 3 sine of stuff would normally be 3, but it's 4 here. So that tells me that it's been shifted up by 1. So that seems to be the answer, but A equals, okay, which some people put, but here's why that's not the answer. 3 sine of, okay, sine x looks like this. If you stretch that by a scale factor of 3, you make it look like this. And then that 2 there just squashes that in, and the 1 moves it up, but it still is going up first and then down. Ours goes down first, then up. And what that basically means is the whole thing got flipped upside down, and that actually means that A is -3. That doesn't mess up anything else. A -3 still gives it a range that's 3 times bigger. It just flips over the minimum maximums. So that was a really tricky one, but yeah, I suppose just watch out in those sorts of questions if it appears to be going down first instead of up first. Similarly, a cos, if there was the same kind of thing for cos, you would expect cos to look like that, but if you saw that it was looking like that, you would know that some kind of flip had gone on. Okay, I'm going to skip over this name of time. Well done, Harry and Terence. Okay, quick plug for my stuff. If you don't already have my complete A-level maths course, go for it. You can get 30% off on that. I've got my A-star course as well. I'm really happy with that. It's got all of the pure, most of the mechanics and most of the stats now. Some more mechanics and stats are coming. That's basically working through all of the hardest stuff. Absolute top end. That's for people aiming for A-star. So do go for that. You can use the code A-star for 30% off that. As before, you can find a link to give a donation if you fancy in the description. Right, final style. I want to look at problem solving. So these questions are common and they are not answered well. People don't tend to get most of the marks in these. So I want to talk through a few of these. So these are often a multi-part question. For example, starts gently. For example, fully factorize this. Well, we can pull out an x, giving us x squared minus 4. We can then notice that that's the difference of 2 squares, giving me x and then x minus 4, x plus, whoops, that's wrong. Don't make that mistake. That should be 2 and that should be 2. So there's the fully factorized version, hence sketch this graph. Okay, well, we can sketch that as a cubic with roots at 1, 2, and -2. So mark in my roots, -2, 0, -2, and 2, and it's a positive cubic. So it's going to look like that. It's going to go up through there, down through there, up through there, and away. Okay, we're done there. Now here's the tricky part. G of x is x minus p cubed minus 4x minus p. So that is a transformation of this. Now it says, given that the point 1, 0 lies on g of x, find the possible values of p. All right, so we've got to establish what sort of transformation this is. The key fact here is to notice that that is, if f of x is our original function, then g of x is simply each of these x values replaced by x minus p. So that's f of x minus p. So that's a translation of p units to the right. So the question is, by how much do we need to move it to the right to make the point 1, 0, which is here, sit on the graph? Well, you kind of got to imagine the graph moving about. And hopefully what's going on in your mind, and I'll show you this in Desmos in just a moment, is that if you slide the graph 1 unit to the left, this point ends up there. If you slide the original graph 1 unit to the right, this point moves there. And if you slide the graph 3 units to the right, this one goes there. So there actually should be 3 values of p. So we could move it. So this one here would be 1 unit to the left, which means that p would need to be minus 1. This one is 1 unit to the right, which means that p is 1. And this one is 3 units to the right, which means that p is 3. Don't try to do that one algebraically. For example, I wouldn't suggest subbing in the x equals 1, y equals 0 into here. You'll just get a big messy cubic in p and it'll be a bore to solve. Okay, let's see if I can show you this in Desmos. With these sorts of questions, let's see, do we have this? I would really strongly suggest you guys do play around with Desmos, because it's so good for building intuitions. I know you can't use it in the real thing, but it's just fun to use. So you can just key in a question like this almost exactly. So y equals, and it was x minus p cubed minus 4x minus p, and it's going to just add a slider. And now I can slide this around and see what happens. And what was our point? Our point was 1, 0. So what did p need to be? Well, if p is that minus 1, it sits on that point. If p is 1, it sits on that point. And if p is 3, it sits on that point. So it's really fun to play around in Desmos with these sorts of things. Just go to, just search for Desmos. It's free and it's quite easy to use. Let's have a go at another one involving a stretch. So f of x is x cubed minus 9x squared plus 24x minus 16. Show that x minus 4 is a factor, hence fully factorized. So this is just a bit of algebraic division. I'm not going to skip over A, but I'm going to explain what you do, which is you work out f of 4, you actually sub it in, you show yourself subbing it in, 4 cubed minus blah, 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 and you show it 0. That shows that x minus 4 is a factor. Do write that as a conclusion. You literally get a mark for that. Therefore, x minus 4 is a factor. Hence, fully factorize f of x. So that's just doing algebraic division. I like grid method for this. If you don't, that's fine. So what I'm doing here, if you do long division, you'll get exactly the same result. So here's how I'd approach it. I'd be saying I need x times something to give me x cubed. So that'll be x squared. That gives me my x cubed here. Whoops, I got that wrong. Other way round. I want x squared up there, giving me an x cubed in here. So x squared times x is x cubed. That gives me a minus 4x squared. What did I want? I wanted minus 9x squared, so I need a minus 5x squared here. That means it's a minus 5x there, giving me 20x here. I wanted 24x, so I need another 4x here. So I must have had a 4 here because 4 times x is 4x, and that gives me the minus 16 that I wanted. So I now know that the fully factorized, oh no, not fully factorized, the partially factorized form is x minus 4, and then x squared minus 5x plus 4, and now I can just factorize that quadratic. So that quadratic is x minus 4, x minus 1. So the x minus 4 can just square here, x minus 1. So there's the fully factorized form. Okay, now onto the tricky problem solving bit. The point 20 lies on g of x. Find the possible values of k. Okay, a sketch is going to be very, very useful here. So I would be sketching this graph, and that's a positive cubic with one standard root at 1 and a repeated root at 4. So we've got a positive cubic. It's going to cut through at 1, and it's going to bounce off the axis at 4 and go away like that. Now we want some kind of stretch in the x direction to make it go through the point 20. Okay, so what sort of stretch gets the 1 over here? Well, that'll be something that doubles the x values. And we would want an f of half x transformation to do that. So one solution is going to be k equals a half. What sort of transformation gets the 4 back to 2 there? Well, that would be one that halves the x values, which is f of 2x. So that would be a k equals 2 transformation. Again, you can play around on Desmos to kind of get your head around that, but that's quite again, like quite a nice sort of, it's not super common, but it's come up a few times, a sense of figuring out what sort of transformation puts your makes your transformed graph go through the point you want. Okay, final type of problem solving question here is one of these. So f of x is this cubic. It says find the coordinates of the stationary points. So this is going to be differentiation. This is the sort of thing which hopefully by the time you've done loads of year 13 differentiation, this feels like 3 marks, hopefully. We just concentrate. So 6x squared minus 18x plus 12 equals 0. I know that simplifies. We could be dividing by 6 there, but laziness and desire to definitely not make a mistake compels me to use my calculator. I'm getting x equals 2 and x equals 1. But I want the coordinates, so I'm also going to be subbing those into the original. So when x equals 2, I've got 2 times 2 cubed, minus 9 times 2 squared, plus 12 times 2, and I get y as 4. And when x equals 1, I get 2 times 1, minus 9 times 1, plus 12 times 1, 5. So my coordinates are x equals 2, y equals 4, and x equals 1, y equals 5. Okay, so I have the coordinates of the stationary point. Now they're saying, given that the curve y equals 2x cubed minus 9x squared plus 12x plus k has exactly one real root, find the possible values of k. Maybe your mind is going towards discriminants because exactly one real root sounds a little bit like discriminants, but we definitely can't do that because this is a cubic and discriminants only work defined for quadratics. You basically got to sketch this and figure it out by looking at it. So let's do that. We have a positive cubic equation with 2 stationary points. And the stationary points are at 1, 5, so that's here, and at 2, 4, which is here. Now it's a cubic equation that actually goes through the origin. When x is 0, y equals 0. So it need to draw it very steeply. So it goes up here, hits its maximum point, hits its minimum point, and then goes away like that. So that's the original function. But then we've got this transformation, and what is that? Well, that is just f of x plus k. So that is a translation in the y direction. Now, we want to guarantee that when we move this up and down, we'll only have one real root. So what you need to be thinking is, well, where could I ever not have one root? At the moment, I've got one real root. If I slide this down, well, if I slide it down enough, I'll start getting more roots. For instance, I might slide it down so that this one here just touches there. And if I do that, I've suddenly got two roots. So how far would I need to shift it down to do that? Well, currently the y value here is 4. So if I shift it down by 4 units, so if k is minus 4, I've suddenly got more than one root. If I keep on shifting it down, I could shift it down so far that I've got 3 roots like this. If I shift it down a little bit more, I'll have 2 roots like that. And then finally, if I shift it down by enough, I'll have just 1 root again. So how far would I need to shift it down to get this point here? Well, the y value up here was 5. So I shift it down by 5, it will be on that cusp there. So if I shift it down by more than 5 units, I'll be okay. And if I shift it down by less than 4 units, I'll be okay. So what does that tell me? Well, shifting it down by 4 units would be k is minus 4. And if shifting it down by 5 units would be k equals minus 5. So if k is more than minus 4, it means I'm not shifting it down that far and we'll be all right, just one real root. And if k is less than minus 5, it means I've shifted it down by more than 5 units and I'll be okay again. So these are the possible values of k. That, I think, is something which is worth just taking a look at on Desmos. Again, you don't get Desmos in your exam, but the more you use it, the more it will feel intuitive, these sorts of things. So what was my function? My function was y equals 2x cubed minus 9x squared plus 12x plus k, and it was going to create the slider for k. And what we can see here is that as I slide it about, I definitely just have one root. But if I slide it down, still got one root, but as soon as I go between minus 4 and minus 5, it's suddenly got more than one root. But if I go and shift it down by more than minus 5, now it's got one root again. So to get that question, we absolutely have to be having a sketch for our original function up here, and then just thinking about what happens as we shift it down. Some people find it easier, some people find it harder, sort of imagining a graph sliding up and down like that. But if you find that difficult to visualize, you can always just draw in the kind of critical points like I did. Okay. One more question. I know we're kind of out of time, but stick around if you want to. No, you know what? I'm not going to go over this. There it is on the screen. You can feel free to try this yourself. I don't want to go over too much. I want to give time for questions. So there's a worksheet, link in the description, which kind of helps you practice the stuff that was there today. So feel free to download that. Would be, oh yeah, have a go at this last quiz actually. So a graph of y equals f of x is shown above. The point 20 lies on the curve y equals f of x minus a. Find the possible values of a. So for this one, we're thinking, by how much does it need to shift in order to put the point 20 on it? So I'm seeing it's got to shift either 1 unit to the left or 4 units to the right. So that gives us this one. Well done. All right, let's just wrap things up there. I'm going to skip over this one. Well done, Tarry. Cool, I'm not going to work through that. Cool, that's it for today. I'm going to stick around for another few minutes, so if you have questions, that's fine. I know that Anna had a question which I'll come to. So if anyone else has any questions, feel free to ask. Otherwise, thanks very much for joining. I'm not quite sure when I'll be doing more of these revision sessions. I'll send out messages when I do. Might be doing more closer to exam time. So thank you very much for joining, and do look out for more live sessions going forwards. But yeah, feel free to ask any questions you've got in the chat, and I will answer your question Anna had as well, which was, so could you do a graph for the previous function, the inverse transformation for the graph? Yeah, do you want to just I'm not quite sure I understand that question. So give me just maybe ask it again, and I'm happy to answer it. Maybe not there anymore. Anyway, we'll leave it there then. Well, thank you very much for joining me. And if you're watching this in the recording afterwards, thanks for watching. Do look out for future revision sessions, which I'll be putting up closer to the time most probably. So that's all. Thank you very much for joining me, and I'll see you guys soon.